This video, as per request, is an amount of substance worked example. So this is the question we're going to be looking at, and this is the entire question, so it's made of 3 parts and is overall out of 8 marks. So this is the first part of the question, and this is my worked solution, and we'll go through that now. So the question, part 1, sodium carbonate is produced in large quantities by the Solvay process. In this process, ammonia and carbon dioxide are passed through a solution of sodium chloride, forming sodium hydrocarbonate and ammonium chloride in this equation here. And this will be important when we're looking at molar ratios. The next stage, sodium hydrocarbonate, is thermally decomposed to form sodium carbonate. So we're taking one of our products from here and putting it back into an equation. And then the question is, calculate the maximum mass of sodium carbonate, which theoretically could be obtained from 546 kilograms of sodium chloride. So how much of this product can we theoretically make when we're given this quantity? So it's theoretically because in practice you can lose product via side reactions or by when you transfer your reactions, you can lose product on the reaction vessel. So it's theoretically how much can be obtained. So now we start the calculation. So we first want to calculate the moles of sodium chloride because this is the mass that we've been given. And we're calculating the moles because the moles allow us to find molar ratios between sides of the equation. And this will allow us to eventually find the mass of the products. So we're going to calculate the moles of sodium chloride. So we're using our equation here. So we have moles equals mass over relative atomic mass or relative molecular mass. And in this case, it's molecular mass because we have a molecule of sodium chloride. So we have our 546 kilograms on top and our relative molecular mass on the bottom, which is our 23 for our sodium and 35.5 for chlorine. And when we plug this into the calculator, we get 28/3 moles of sodium chloride. And if we look at our equation that we're given at the top, we have a 1-to-1 molar ratio between our sodium chloride and our sodium hydrogen carbonate. And this is because they have the same number coefficient out the front of the molecule. They both have a 1. So we know that we have a 1-to-1 molar ratio, so that means that we also have 28/3 moles of sodium hydrogen carbonate. And then we want to take this sodium hydrogen carbonate that we have made and we want to plug it into another equation where we thermally decompose it. And this is what the question is telling us. But you can see out here that our 1 from over here has now changed to a 2. But just because the molar ratio changes, it doesn't mean that our actual mole value has changed. It just means that the molar ratio has changed in proportion to the other products formed. So we still have 28/3 moles of sodium hydrogen carbonate. It's just relative to the other products formed, it is a 2. So this means that we have a 2-to-1 molar ratio between our sodium hydrogen carbonate and our sodium carbonate. So this means that we can divide our 28/3 by 2 to get our moles of sodium carbonate, which is 14/3. And then we want to rearrange the equation that we've used at the beginning, and we want to rearrange it to find mass. So we have our moles equals mass over mR, and we can rearrange it to our mass equals moles times mR. So we now have our moles of sodium carbonate because we've just found that 14/3, and then we can times it by its molecular mass, which is here, and this gets us 494.67 kilograms, which we can round to 494.7 kilograms. And this will get us our 4 marks. And then moving on to part 2. So we have 100 centimeter cubed of standard solution of sodium carbonate. And this was produced by dissolving 0.5 537 grams of sodium carbonate in water in a volumetric flask. Calculate the concentration in moles per decimeter cubed of the sodium carbonate solution, and this is 2 marks. So we first have to think, what is our equation for concentration and what are the units we need? So our equation for concentration is moles over volume, and it's given us in the question that it wants a concentration in moles per decimeter cubed. So this means that our moles must be in, obviously, moles, and our volume, it wants us to have it in decimeter cubed. So first we want to calculate the moles of the sodium carbonate that we've dissolved in our solution. So we want to find the moles, so we're using this equation here, our moles equals mass over mR. So we plug the values that were given in the question, so we have our 0.537 grams, and we're dividing it by our relative molecular mass, which we know now is 106, and this gets us our moles here. So this is our moles that we've dissolved in the solution. And then we want to convert our volume into the correct units, because we are given the volume here. We're given that it is dissolved in 100 centimeter cubed of water. However, this is in centimeter cubed, and we want it in decimeter cubed for our correct equation and concentration. So we know that 1 decimeter cubed equals 1000 centimeter cubed. So we can use this equation to divide our 100 centimeter cubed by 1000 to get that we have 0.1 decimeter cubed. And then we just need to plug both of the values that we found into the equation. So our concentration is the moles over the volume that we've calculated, getting us 0.0507 moles per decimeter cubed, and that is the concentration of our standard solution, and this would get us our 2 marks. And finally, the last part of the question, part C. So carbon dioxide gas can be absorbed by sodium hydroxide solution as shown by the following equation. So this is our equation here of carbon dioxide gas being absorbed by sodium hydroxide solution. So it's asking us to calculate the concentration in moles per dm cubed of sodium carbonate in a solution formed by dissolving 2 grams of carbon dioxide in 200 centimeter cubed, an excess of aqueous sodium hydroxide. So it's asking us to find the concentration of sodium carbonate in this solution that we've formed. So we first have to look at what the question has given us. It said that our sodium hydroxide is in excess. So this means that our carbon dioxide is the limiting reagent. So this means that it's the amount of CO2 that determines how much product is made. So this means if sodium hydroxide is in excess, not all of the sodium hydroxide will be used to make our product, but all of the carbon dioxide will be used because it's the limiting reagent. The reaction will keep going until the carbon dioxide runs out. So it's our carbon dioxide that determines how much of our sodium carbonate is formed. So this means that to find the correct molar ratios, to find our concentration of sodium carbonate, we must calculate the moles of CO2, not sodium hydroxide. So we calculate our moles of CO2 by our equation, moles equals mass over mR as before. So we have our mass of 2 grams and we have our molecular mass of 12 plus 32 for our carbon and our 2 oxygens. And this gets us a mole value of 1 over 22. And then we look at our molar ratios again, and we have a molar ratio of 1 to 1 because both the coefficients out the front of the molecules are 1. So this means that we also have 1 over 22 moles of sodium carbonate. And then we again want to convert our volume into the correct units because it has given us in the question that it wants the concentration in moles per decimeter cubed. So we have our moles, and now we need to convert our volume of 200 centimeter cubed into decimeter cubed. And as we showed in the last slide, we do this by dividing by 1,000. So this gets us 0.2 decimeter cubed. And then we want to plug the values that we found into our equation of concentration equals moles over volume. So we have our moles of 1/22, we divide it by our volume of 0.2 decimeter cubed to get us our overall concentration of 0.227.